Ladies and gentlemen, welcome. So today we will solve only problems, and I would like to go over the last problem that from the previous video. Unfortunately, the video was cut off early, and I didn't have a chance to finish the problem, the last problem. And in this lecture, we will talk about, we'll solve that particular problem using exponentials and equations, and also we'll be solving some other problems involving limits of functions and continuity of functions. All right, so let's get started. Let me start first with the problem from last lecture, and that is the following. So problem 1. So I started to solve that problem, but I didn't have a chance to finish it. I don't know, for some reason the video was cut off early. I don't know why. All right, so the problem was the following. Solve the following equations. And the first one was the cube root of 2 raised to the power x plus 10 equals 2x squared. The second one was e to the power 2x plus 3 equals 1. And the last one was something like this: e to the x squared over e to the x plus 10 equals 1. Okay. So we will solve these three equations, and just like I said in the I started doing so in the previous video, but let me do it again. All right, so let's look at the first one. So if you look at the first one, you have this guy here, this cube root of 2, and here you have a 2. So you kind of want to make the left-hand side, you try to make it look like something similar to the right-hand side. So maybe we should do something about it. And if you look at it, you can write this guy. Okay, we write. Oops. The cube root of 2, everything raised to the power x plus 10. We write this as, so pay attention here. So we're going to write the cube root as 2 to some rational power, right? So keep in mind that we have the following rule here. I'm just gonna say it. The nth root of a to the power m is nothing else than just a to the power m over n, right? So we can write we can write the nth root as a rational power. All right, let's use this here. So this will be 2 to the power x plus 10, everything over 3. Wow. So once we have this, our equation becomes the following: 2 to the power x plus 10 over 3, everything over 3, equals to 2 to the power x squared. So now, as you can see, these are two exponentials. They have the same base, as you can see here. So this will attract immediately. So this implies that x plus 10 over 3, everything over 3, is the same as x squared. Or if you want, if we do the computations here, or equivalently, we have that x plus 10 is the same as 3x squared. And now this is just a quadratic equation for 3x squared minus x minus 10 equals 0. So now we have this quadratic equation, and we need to solve this. Well, you can even use the quadratic formula if you want, or you can just try to factor it somehow. It doesn't really matter which way you want to do it. In fact, you know what? Let's use the quadratic formula. So now the discriminant of the equation is, so let's call this equation E. And the discriminant is given by, let's say call this delta E of the equation E. And this will be -1 squared minus 4 times 3 times -10. Right? So this will be, oh, sorry, here is a minus. So this is 1. And this guy will be, so it will be 121. Which is positive, so we will have 2 roots. So x12 will be nothing else than my -1, so 1 plus minus square root of 121, right? Everything over 2 times 3, which is 6. But the square root of 121, as you will know, is 11, so this will be 1 plus minus 11, everything over 6. And from here we have 2 solutions. So let's look at them, x1 and x2. So x1 will be 1 plus 11 over 6 will be 2. And the second one will be -10 over 6, which will be -5 over 3. So these are the solutions for our equation, right? And we would like to see which one works. Well, if you plug in 2, clearly this works, right? This is good. But anyway, I'll leave it to you as an exercise to see if this one is good or not. So I'll leave a question mark to you here. All right. Now let's see the second one. The second one was, so the question is, so is e to the power 2x plus 3 equals 1? Well, the thing now is that we would like to write this one as, you see here I have the exponential in base e, and this guy is just 1, so maybe I can write this as e to some power, and indeed I can do it. It's e to the power 0. So this follows that our equation is equivalent with the following, with e to the power 2x plus 3 is the same as e to the power 0. So now, as you can see, we have the same base. If you look here, e is the same as here. So this will imply, this implies that (2x plus 3 equals 0), or x is -3 over 2, and that's it. And now the last one is pretty similar, but here we have to do some kind of an operation. So the equation, let's write this expression. So we write e to the power x squared over e to the power x plus 6. I believe that was it, right? Let me look. Oh, plus 10, I'm sorry. Plus 10. Okay, plus 10 anyway, it doesn't matter, equals 1. Here we go, the same story again. You can, of course, this you can write this as oh, sorry about that. We write this as e to the power x squared minus x minus 10, and our equation is equivalent with, so keep in mind that we have that, so e to the power x squared minus x minus 10 is the same as the same as 1, which is e to the power 0, or x squared minus x minus 10 is 0. So we have a quadratic equation again, and then I will leave this to you as an exercise to prove it. Anyway, I don't want to lose time in computing all these numbers here, right? Okay, now let me veer towards something else. Problem 2. Which says the following. In fact, I will compute the following limits. So we would like to compute the limits. And the first one is limit as x approaches -3, let's say, of 3x plus 9, everything over x squared minus 9. The second one is lim as x approaches 3, that's 3x plus 9, everything over x squared minus 9. And maybe, let's say another one, c lim as x approaches 0 of x times x plus x to the power -1. So let's put it this way. And now the last one, d, is limit as x approaches 0, and this will be a little bit tricky, x over the absolute value of x. All right, we'd like to compute this 4 limits. Look at them. So let's see. The first thing that you need to do, let's start with the first one. And the first thing that you need to do is, you see, you have here x approaches -3. So the first thing you need to do is to plug in, so to x equals -3 into this fraction here. So you plug it in here. So this is what we call the direct substitution. So let's do it. So using direct substitution, we have the lim as x approaches -3 of 3x plus 9, everything over x squared minus 9. This will be nothing else than just if we plug that in here. This is 3 times -3 plus 9, everything over -3 squared plus 9. But this guy here, so it will give us what? Well, if you look, it will give us, so -9 plus 9 over over 9 plus 9. Sorry, negative. Yes, negative 9 plus 9. It will be. So as you can see here, I'll have 0 over 0. So this is an indeterminate, right? It's undefined, this guy here. we need to do something about it. Well, you'll see that we will you can deal with this kind of limits when you learn about differentiability in a heartbeat using what we'll call the L'Hopital rule, but anyway, we don't know that till then. So we need to come up with something. Maybe we can get rid of something, and yes, we can. So now we can simplify things a little bit. Now the limit as x approaches -3 of 3x plus 9 over everything over x squared minus 9. This can be, we can factor things out here. So this will be the lim as x approaches -3 of 3 times x plus 3. So we can factor 3 on top. And now we can factor this guy on the bottom and this way. X minus 3 times x plus 3. And now guess what? Look at these guys. How they go away? And this will be nothing else than just the limit as x approaches -3 of 3 over x minus 3. Well, and if you look at this, if you plug it in, this is nothing else than just 3 over -6, which is -1/2. So that's the limit for the first one. Now let's look at the second one. So the second one was the limit. So again, we will have to look at this a bit. So we would like to, so we have the limit as x approaches 3 of 3x plus 9. Pay attention now, over x squared minus 9. So it's the same thing, but this time we're approaching 3, positive 3. And this, again, we can plug in the value 3. So once we plug in the value 3, unfortunately, we'll get again 0 over 0, which is undefined. But we have seen previously that we can do this trick. We can factor things out. And we can write this limit. So this time will be limit as x approaches 3 of 3x plus 9, everything over x squared minus 9, right? And we can factor this, if you look at it. So this would be on top 3 times x plus 3, and this would be x minus 3 times x plus 3, which is nothing else than just the limit as x approaches 3 of 3 over x minus 3. Well, surprise, surprise. Now, if we plug it in, x equals 3, this will give us nothing else than just 3 over 0 by direct substitution. Well, now the question is 3 over 0 depends. If you approach 3 from the left, it will be negative infinity. If you approach 3 from the right, it will be positive infinity. And maybe we can say that, so this is plus minus infinity if you want. So we can say the limit does not exist. Well, you can say it's infinity, but if you want to be very particular about this, you can say that the limit does not exist, right? Depends. If it's 0 minus 0 plus, whatever. All right, now let's see the third one. So we are interested in, well, again, so we have, let's write this limit. Lim as x approaches 0 of x times, sorry, I think it was 1 here. Let me check. Here it's 1, not x, sorry about that. So this would be 1 plus x to the -1, and this will be nothing else than just the lim as x approaches 0 of x times 1 plus 1 over x. Well, again, direct substitution doesn't work, right? Because you have 1 over 0, which is not defined. So we need to do something about it. And maybe we can work things out. So this will be nothing else than just the lim as x approaches 0 of if we do the operations here, it will be x plus 1 plus x over x. Let me put it this way. But which is nothing else than just the lim as x approaches 0 of x plus 1. And now we can plug it in. We can use the direct substitution, and this will give us nothing else than just 1 plus 0, which is 1. And now the last one, and I said this was a bit trickier. We need to take care of, so we need to find the limit as x approaches 0 of x over the absolute value of x. So now let's use the definition of the absolute value of x. So let me recall that the absolute value of x is nothing else than just plus x if x is non-negative, right? So I include also 0, and negative x if x is negative. Okay, and now, of course, since I'm at this point, I'm forced to take the limit from the left and from the right. So the left-hand side limit and right-hand limit. And now I will have the following. So this implies that the limit as x approaches 0 plus of x over absolute value of x is nothing else. So keep in mind that the 0 plus is the limit as x approaches 0, but from the right. So this would be the lim as x approaches 0 plus. Keep in mind, okay, let me just say it again here. This guy here is nothing else than just x approaches 0, but x is greater than 0. So keep that in mind. So this will be x. Well, in this case, x will be nothing else than just the absolute value of x will be positive x, so it will be x, and this guy will be 1. So this guy is 1, right? And we also have that the lim as x approaches 0 minus, and in this of x over absolute value of x is nothing else than just lim as x approaches 0 minus from, and now we should look at this guy, look at this guy, and this is nothing else than just x approaches 0 and x is less than 0. So keep that in mind. So this will become the following. So it's x over negative x, which is negative 1. Well, guess what? The two limits from, so this first one, these two limits do not agree. From the left and from the right, they don't agree. So it follows that the limit, so the lim as x approaches 0 from the right of x over absolute value of x is not the same as the lim as x approaches 0 from the left of x over absolute value of x. So the lim as x approaches 0 of x over absolute value of x does not exist. And we can also see, let me point out the remark here. We can see this graphically as well. If you want to see a picture, you can see it very clearly. So let me draw the picture so that you can guys see this clearly. So as you can see here, I have this, so here is negative 1, here will be at 1, so then here will be this limit as x approaches 0 plus of x over absolute value of x, and here will be this guy lim as x approaches 0 from the left of x over absolute value of x. And I think this this picture makes complete sense when you look at it, right? All right, now let's compute more limits. I'll try to separate, to do more exercises, not just one with 10 limits. So that was problem number 1. I think you got the gist and everything. What's going, you can see, well, this is just a warm-up, right? So this is the problem. Now let's see something a little bit more involved. Problem 3. Okay, so problem 3, the same thing, compute the following limits. And the following limits, so let's see, the first one we would like to compute is the following. So lim as x approaches 2 of x minus square root of 2 plus x, let me write it in this way, everything over x minus 2. That's the first one. The second one is the limit as x approaches 3. Let me look. Of this rational function, x squared plus 3x minus 10, everything over 3x squared plus 5x minus 7. The third one is the limit as x approaches 6 of tangent of pi over x, everything over x minus 1. And D, this will be the lim as x approaches 0 of x plus 1 squared minus 1, everything over x. All right, so these are the four examples that I would like to solve. Now, as you can see, this problem is very similar with the previous problem. So let's look at it a bit. Okay. Now, let's see. So let's look at the first one. As you can see here, I have a fraction, and on the top, so on the numerator, I have a radical. So maybe but first, let's plug in x equals 2. So we have that the limit as x approaches 2 of x minus square root of 2 plus x, everything over x minus 2. Well, and now we can plug in x equals 2, so let's do that. So you will get 2 minus 2 plus 2, everything over 2 minus 2. And again, we'll get 0 over 0, which is undefined. So we need to take care of this. So we have this indeterminate, this is how we call it, or it's undefined. You can simply call it like this. So we need to get rid of it. So how should we get rid of it? Well, when you have radicals, there is this procedure that you learn in college algebra, which is called you multiply by the conjugate. And let me remind you this. Multiplication by the conjugate, what does it mean? So if I have, let's say, the square root of a minus square root of b, so what I'm doing here is I'm multiplying by the conjugate, which is, okay, let me write with a different color, which is square root of a plus square root of b, so that's the conjugate. And what I get is, I'll get a fraction on the top, I'll have square root of a minus square root of b times square root of a plus square root of b, and everything over square root of a plus square root of b. But now the top will give me nothing else than just a minus b, and on the bottom I'll have square root of a plus square root of b. So that's the conjugate. So it's a procedure that will allow me to take the square root from the top and put it to the bottom. I think that's the procedure. And similarly, if you have so similarly, you can have something like this: square root of a plus square root of b. So in this case, you'll multiply by the conjugate, which is square root of a minus square root of b, and you'll get the same thing. So you'll get square root of a plus square root of b, and square root of a minus square root of b, and this time we'll get square root of a minus square root of b. So it will be the same thing, almost, except that you will subtract the two square roots on the bottom, right? Okay, so that is the multiplication by the conjugate. So you should know this from college algebra, but anyway, I wanted to remind you. But this is the first and the last time when I will remind you this. So I hope it makes. I want you to look clearly at it, and I hope it makes perfect sense. So each time when you have something with square roots with radicals, please think of this. So this is the first thing that should come into your mind. Okay. Now, let me go back to our problem. As you can see, I have this undefined here, right? So this is 0 over 0. And now what we're going to do, so we should multiply by the conjugate. So multiplying by the conjugate, we have, so let's see. So we have lim as x approaches 2 of x minus square root of 2 plus x, everything over x minus 2. So now we're going to multiply by the conjugate, which is given by this guy. So it will be x plus square root of 2 plus x. And this will be equal to lim as x approaches 2 of x plus square root of 2 plus x, x minus square root of 2 plus x, everything over x minus 2 times x plus square root of 2 plus x, which is, and now the lim as x approaches 2, these two guys will give me x squared minus 2 plus x, everything over x minus 2 times x plus square root of 2 plus x, right? Okay. And this will be nothing else than just, let's look at it carefully, the lim as x approaches 2 of x squared minus x minus 2, everything over x minus 2 times x plus square root of 2 plus x. And now there is something we need to do here. Maybe we can, you see on top we have this quadratic, if you look here, you look at this guy, maybe I can factor this in linear terms, and I can actually do it. So this would be nothing else than just lim as x approaches 2 of x minus 2 times x plus 1 over x minus 2 times x plus the square root of 2 plus x. And now guess what? These two will go away, and this will be nothing else than just the limit as x approaches 2 of x plus 1 over x plus the square root of 2 plus x. And now I'm in a good position. So maybe I should plug in x equals 2, and let's see what do we have. So we have 3, and here we have 2 plus 4, square root of 4, which is 2, 2 plus 2, which is 4. So the value of the limit is nothing else than 3 over 4. All right. So that was it was a bit involved, but that's the technique. And now the second one. So let's always, when you have a limit, you try direct substitution all the time. So you might get a value in case in case when you try the direct substitution, it will give you something that is undefined. Then you need to look further for some other techniques. Now let's look at the second limit. So we have the limit as x approaches 3 of x squared plus 3x minus 10, everything over 3x squared plus 5x minus 7. Right? Okay. Now, the first thing, like we said, we're going to try direct substitution. So this would be, let's plug it in. If you try direct substitution, this will be 3 squared plus 3 times 3 minus 10 over 3 times 3 squared plus 5 times 3 minus 7. And guess what? This will give us 27, 8, okay, 8 over 35. Ooh. Okay, we're done. That's the limit. We got the finite value, so we're happy with it. So we don't need to do anything else, any fancy stuff. And now let's look at the same thing we're gonna do for the tangent. So we have that, and we would like to see if we obtain a value as well. We have the lim as x approaches 6 of the tangent of pi over x, everything over x minus 1. Okay, let's do the same thing. We plug in x. You see, I have a fraction here. So 6, it won't give me any headaches. The only number that would have given me headaches would have been 1. Because you see that the bottom, so the denominator has a problem when x equals 1. So it will be 0. So, you know, fractions with 0 denominator don't quite actually exist, but anyway. So, but this time, as you can see, it's that guy is 6, is not 1, so we are in a very happy situation. So this would be nothing else than just, when you plug it in, it will be tangent of pi over 6 over 6 minus 1, and tangent of pi over 6, right? If you go back to the trigonometric table that we have talked about in the first or the second lecture, it was nothing else than just 1. So it was 1 over square root of 3. So it will give us 1 over 5 square root of 3. And that's it. And now the last one, we have, let's see the last one. So the last one was something like this. Let me look. Okay. So it was lim as x approaches 0 of x plus 1 squared minus 1, everything over x. All right. So let's look at this limit. Let's plug in x equals 0, right? Keep in mind that x goes to 0 here. So we're going to plug it in here and in here. So if this would give us, let's see, it will give 1 squared minus 1 over 0, so which is 0 over 0, which is again undefined. So keep in mind that 0, when you divide 0 by 0, that's undefined. So maybe we should do something about it. Well, again, some college algebra comes into rescue. So we have that limit as x approaches 0 of x plus 1 squared minus 1 over x will be nothing else than just the limit as x approaches 0 of well, you can expand this, or you can just, so it's x plus 1 minus 1 times x plus 1 plus 1, everything over x, which is equal to lim as x approaches 0 of x times x plus 2 over x. And finally, these two go away, and this will be nothing else than just the limit as x approaches 0 of x plus 2. And now we can safely plug in x equals 0, and this will give us 2. And that's it, right? Okay. Now I would like to compute some other, now a little bit more fancy limits. So problem number 4, I'm sorry. Because I want to show you a variety of problems and how to deal with them. So compute the following limits. The first one is lim as x approaches -2, and pay attention now, of the absolute value of x plus 2, everything over x plus 2. The second one will be lim as x approaches 0 from the right of sine of x over square root of x. And the last one is the lim as x approaches, let's change now to t, of tangent of 5t over tangent of 2t. So these are the limits we want to compute. I want you to look at the problem. Okay. Let's start with the first one. And again, since we have something with absolute value, maybe it's a good idea to write a definition of the absolute value. So we have that the absolute value of x plus 2, it will be, and I want you to be very careful here, it will be plus, I'm going to write it in this way, x plus 2, if the quantity x plus 2 is non-negative. It will be minus quantity x plus 2 if the quantity x plus 2 is negative. And now let's rewrite this a bit, or equivalently, we can say that the absolute value of x plus 2 will be equal to x plus 2 if x is greater or equal than -2, and negative x negative 2 if x is strictly less than -2. So this is how we can write the absolute value of x plus 2. Okay, and now what we're going to do, we're going to compute the limit. So, but you see, I have the limit, keep in mind that I have the limit as x approaches -2. And now since the quantity on the top is the absolute value of something, maybe I should look, and you see here I have a problem when x is, so maybe I should look at the left-hand limit and the right-hand limit. So let's do that. So we have that the limit as x approaches 2 from the left, 2 minus, right, of absolute value of x plus 2 over x plus 2 will be, so keep in mind, again, let me remind you that this guy here is nothing else than just x approaches 2, but for values less than 2. So this would be equal to negative x plus 2 over x plus 2. And if you, this will give us -1. And the second one, the limit as x approaches 2 plus, so 2 from the right. Let me say this again. For values greater than 2 of the same quantity, so I'll have the absolute value of x plus 2 over x plus 2. This will be the lim as x approaches, I think it was negative, oh my goodness, it was negative 2. Sorry. Right? Anyway, it doesn't really matter. This is negative 2 on the right. So let me, so this is negative here. Right? Okay. So this would be nothing other than just x plus 2 over x plus 2. And this will be nothing other than just 1. As you can see, these two do not agree. So the limit does not exist. So the limit, and we can write this lim as x approaches negative 2 of the absolute value of x plus 2 over x plus 2 does not exist. Okay. Now let's see the part B. And now let's look at this guy. So we have the limit as x approaches 0 from the right of sine of x over square root of x. Well, if you plug it in, if you do the same thing, again, you'll get 0 over 0. Sine of 0 is 0, square root of 0 is 0. So again, it's undefined. So maybe you should do something. Does this ring a bell to you? You know, we have that limit. So remember that the lim as x approaches 0 of sine of x over x is 1. Keep in mind that we have this. So we intend to use this, and let's do it. So we have that this guy is the same as the lim as x approaches 0 from the right of sine of x over x times x over square root of x. So let's write it in this way. And this guy will be equal to, we're going right here. And like I said, our intention is to use this limit. So this will be the lim as x approaches 0 from the right of sine of x over x times, and now I'm going to use the product rule. Lim as x approaches 0 from the right of x over square root of x. So here I used product rule. And now this guy, in the virtue of what we previously said, this guy here is 1. And this guy here, if you look at it, this is nothing else than just, let's write it, is 1 times lim as x approaches 0 from the right of x over square root of x will be nothing else than just square root of x. But this guy, if we plug it in, this limit here is the square root of 0, which is 0. So finally, the result will be 1 over 1 times 0, which is 0. And that's it. Right? So that was the, let's say, the trick. I would not exaggerate calling it a trick, but this is when you have something with sine and when you plug it in, it doesn't really work immediately, then you should think of this limit, especially when x approaches 0. So keep in mind this. Okay? And now the last one. So C. It's in a similar fashion with this one. So we have to compute this limit, lim as t approaches 0 of tangent of 5t over tangent of 2t. We have to compute this. Well, if we plug it in, if you look at it, right? And if we plug in t equals 0, right? You will get the same thing as undefined, is 0 over 0. So maybe we should do something about it. So maybe let me remind you something which is similar. So remember that the lim as t approaches 0 of tangent of t over t is 1. So it's the same thing as for sine. And we would like to use this, but pay attention because the expression is a bit different. So maybe we can write this fraction in the following way. So write tangent of 5t over tangent of 2t as we'll write it in this way, tangent of 5t over 5t, everything over tangent of 2t over 2t. And now let's see, we multiply this. So this would be 5 times 5 over 2. Okay, 5t over 2t if you want, right? So we can write it in this way. And now, clearly, this implies that the limit as t approaches 0 of tangent of 5t over tangent of 2t. Now we can apply the quotient rule as well, if you want. It will be, okay, let me write it in this way, and then I will apply the quotient rule. So tangent of 5t right, times 5 over 2. This t will just vanish here. All right, so we can write it in this way, and now this will be, let's take this constant outside the limit, so it will be 5 over 2 times, and now we'll apply the quotient rule. So here I apply the quotient rule. This will be lim as t approaches 0 of tangent of 5t over 5t over lim as t approaches 0 of tangent of 2t over 2t. But now, in the virtue of what we said here, instead of t, you can put any multiple of t, as long as you have it both on the top and bottom. So in the virtue of what we said, this guy here will be 1. This guy here will be 1. So the final result is 5/2 times 1/1, which is 5/2. And that's the final result. Right? Well, in my notes, I solve it a bit different. I write a tangent of sine over cosine, and then I apply the product rule, but anyway, it's the same thing. Now, I would like to veer towards continuity. So you've seen a bunch of examples of how to prove limits, how to compute limits of functions, but now I would like to use this in a little bit different context. And what I mean by that is the following. So problem 5. Now I'm going to define, let me consider f of x to be equal to x cubed plus 2 if x is less than 2. So I'm going to define a piecewise function 5 if x is equal to 2, and now x squared plus 6 if x is greater than 2. Well, the first task is to find the limit as x approaches 2 of f of x. And the second one is my function f of x, this piecewise function, is f of x continuous at x equals 2. So let's look at the problem. So we will solve a bunch of problems that look like this. This could be like a very good, I would say, midterm exam problem. So let's see. Now, we need to find the limit as x approaches 2, but as you can see here, it's defined with piecewise functions. Look, so I have these, three pieces that glued together will give me my function f. And I'm here I have to compute the limit as x approaches 2. But it doesn't say explicitly 2 from what? From the left, from the right? So we need to figure this one out. So what do we know about the limits of functions? Keep in mind that for the limit at a certain point to exist, the left-hand limit and the right-hand limit, both of them must agree. So we would like to see that. So we have, so let's look at the limit. In fact, let me write it. So we have that the lim as x approaches 2 from the left, f of x. So again, these are the values for which x is less than 2. And we have to look, it's the first piece, so this would be the lim as x approaches 2 from the left of x cubed plus 2, which is, if you plug it in, is 2 cubed, which is 8, plus 2, which is 10. And if we want to look at the limit as x approaches 2 plus of f of x, so 2 from the right, so for values x which approach 2 but greater than 2, so let's look at this. Where is it? Is the third piece. So this would be the limit as x approaches 2 plus of x squared plus 6. Well, guess what? It's 4 plus 6, which is again 10. These two agree. So this implies that there exists the limit as x approaches 2 of f of x, and moreover, this is equal to 10. So that's how we solve the first part. Now the second part asks us if the function is continuous. Well, at 2. Keep in mind that it will ask if the function is continuous at the point x equals 2. And we know this. Let's write this. F is continuous at the point 2, x equals 2. If and only if, so it's an equivalence, the limit from the, okay, let me write it here. So it's if and only if the limit from the left as x approaches 2 agrees with the limit, the right-hand limit of f of x, and moreover, it will agree, and let me write with a different color, with the value of f at 2. So keep in mind that this must happen. So if this happens, then I can conclude that my function is continuous at x equals 2. But now we have seen from previous part that these two guys, the limit, the left-hand limit and the right-hand limit, both of them agree, and moreover they're equal to 10. But now we're left to compute the value of f of 2. So f of 2 is what? Let's see what happens at x equals 2. Well, look, it's 5. And 5 is not 10. So f is not continuous at x equals 10. Sorry, at x equals 2. And that's it. That's the end of the problem. So this is how we solve these kind of problems. Now let me do something a little bit similar, but in this next problem, we would like to determine a constant such that the function is continuous at a certain point. So let's do this. This would be problem 6. Which says the following: find this constant a, right, capital A, which makes the function f of x equals, and this will be piecewise function. It's the first piece is x squared minus 2 if x is less than 1. And the second piece is ax minus 4 if x is greater or equal than 1, which makes this function continuous at x equals 1. All right, so let's look at it. Well, keep in mind, so by the previous considerations, look at this. A function is a continuous at a point, at a certain point, if the limit, the left-hand limit at that point, it agrees with the right-hand limit at that point, and moreover, it agrees with the value of the function at that particular point. So in our case, so we can say that f is continuous at x equals 1. So we keep in mind that we need to look at this point at x equals 1. So f is continuous at x equals 1 if and only if the lim as x approaches 1 from the left of f of x is the same as limit as x approaches 1 from the right of f of x, and is the same as the value of f at 1. Okay, so we must have this. In fact, we know that f is continuous, so we know that this happens, these three conditions. So these three quantities are equal. And now let's compute each and every one of them. We have that the left-hand limit. And now let's look. Is equal to, so let's see, for x equals values less than 1, so it's x squared minus 2. And this guy, if you plug it in, it will give us -1. And then we have the lim as x approaches 1 from the right of f of x, which will give us nothing else than just lim as x approaches 1. And now let's see which piece is the second one. So it's ax minus 4. And once we plug it in, it will give us a minus 4. Okay. And so this is the first one, the second one, and the third one. We have the value of f of 1 is a minus 4. So these three quantities, according to what we previously said, as you can see here above, this must be the same with this. So this guy is the same as with this guy. Well, this guy, these two are. So from here, one can deduce that. So it follows that a minus 4 is equal to -1. Well, from here, it's quite clear that a is 3. And that's it. So only for these, for a equals 3, my function is continuous at 1. And so this is how we solve the problem. Now let's see another one. So this was problem 6, problem 7, because I would like to show you how you can fall into a trap. And let me give you this example, which says the following: discuss the continuity at x equals 0 and x equals 1. These 2 points of f of x is x over x minus 2 if, okay, x is less than 0, 0 if x is 0, 4 over 3x minus 2 if x is between 0 and 1. And the last piece, so you see you have a bunch of pieces here. It's 4 if x is greater or equal than 1. Okay. Oh my. So we'd like to discuss the continuity of this function. You see, we have 2 points here. As you can see, if we look at these pieces, look at this, and now we also have what's going on with these 2 numbers. So let me point them clearly: 0, 0, and 1. So that's why we have these 2 guys here. Right? Please look at them carefully and how the function is defined. Okay. So, well, it's clear what happens to with the values at 0 and 1. Clearly, f of 0 is 0, and f of 1 is 4. Right? As you can see, the last piece is for all values x which are greater or equal than 1. So it takes the value 1. We have this. Now we need to look at the limits, and let's do that. So now we're going to look at the limit as, and now let's study continuity. Okay, let me do it. So the first thing we need to take care of, okay, continuity at the point x equals 0. And now we would like to see what happens with the left-hand limit and the right-hand limit. So we have that the lim as x approaches 0 from the left of f of x is equals with the limit as x approaches 0 from the left. So keep in mind that we have, this happens for values of x which approach 0 but less than 0. And now let's look which one is it. So it's the first one, so it's x over x minus 2. Well, if we plug it in, this will be 0 over negative 2, which is 0. And let's look at the right-hand limit. So this is the limit as x approaches 0, but from the right. So for values greater than 0 of f of x, this is nothing else than just lim as x approaches 0 plus. And now this time will be, let's look which function is. It's, you see I have this part here, which includes values of x greater than 0. So this would be, I will put this function 4 over 3x minus 2. So this will be what is negative 2. As you can see, these two values here do not agree. So the limit as x approaches 0 of f of x does not even exist. So there is no point of talking about continuity. So f of x is not continuous. At x equals 0. Well, what about x equals 1? So maybe something will happen at the, so let's study continuity at 1. At x equals 1, right? Okay, so we have this continuity at 1. Well, we need to do the same thing, but this time we take the limit as x approaches 1 from the left of f of x, which is nothing else than the limit as x approaches 1 from the left of, well, the function we're looking for is 4 over 3x minus 2. And now if we plug in the value, this will give us so 3, yeah, which is 4, right? Okay. And now we're going to take the limit as x approaches 1 from the right of f of x is the same as lim as x approaches 1 from the right. And this time, which is 4, which is 4. Fortunately, these two agree, so the limit as x approaches 1 from the left of f of x is the same as the limit as x approaches 1 from the right of f of x. And moreover, it's something even amazing. We look at the value f of 1 is 4. Wow, it's the same as f of 1, which is, and all these agree to be equal to 4. So we say that f is indeed continuous at x equals 1. And that's it. You see, we have this function was not continuous at the point x equals 1, but it was continuous at the point it was not continuous at x equals 0, but it was continuous at x equals 1. Well, there were some other examples in my notes. I think you can study them. For example, the one that I have in my notes, and I'll leave it to you as an exercise. So this was problem 8. Which says the following, and let us define the following piecewise function, h of x, to be x if x is less than 4 and x over 4 plus 2 if x is greater or equal than 4. And now the question is h continuous on the interval open to 5? So I want you to look at it. Well, the question is, you see, I asked you about the continuity at on the interval 2, 5. So that's not tricky because you see, well, the only number that is giving me headaches here is this number 4. And by the way, 4 is in this interval 2, 5. So if my function f is not continuous at one point from that interval 2, 5, then it's not continuous on that interval. So keep this in mind. So in other words, the only thing you need to do, so let me give you a hint. The only thing we need to do is to study the continuity of my function h at the point x equals 4. And you will proceed in the exact same manner as we have seen in the previous examples. All right, I think I'm going to stop here. This sums up everything we have done for in this second chapter. There will be more videos coming up this next week. And we will start something new, something even more exciting, I would say. We will talk about differential calculus. We'll learn about derivatives. We'll learn about how to compute derivatives using the difference quotient that we have previously seen, even in the first lecture, or maybe even the second lecture and so on. And we will see some how to compute the derivatives of functions using certain rules. And also we will use this notion of derivative in solving real life situations, like we'll see some physics problems and so on. All right, I'll stop here. Thank you very much.